It's a good rule of thumb that in science, the simplest questions are often the hardest to answer. Questions like, how did the universe begin? In fact, until relatively recently, science simply didn't have the tools to begin to answer questions about the origins of the universe. But in the last 100 years, a series of breakthroughs have been made by men and women who, through observation, determination, and even sheer good luck, were able to solve this epic cosmic mystery.
This was real astronomical gold.
I'm going to recreate their most famous discoveries and perform their greatest experiments.
30,000 kilometers per second.
That take us from the very biggest objects in the universe to the infinitesimally small, until I reach the limits of our knowledge by traveling back in time to recreate the beginning of the universe.
The moment 1/1,000,000th of a second after the universe sprang into existence. This is a time before matter itself has formed in any way that we would recognize it. It's as close as we can hope to get to creation, to the beginning of time, the beginning of the universe itself.
It's a remarkable fact that science took hundreds of years to come up with a theory to explain the origins of the universe. All the more surprising given what a simple and fundamental question it is.
There's something quintessentially human about asking the question, where does all of this come from? Perhaps because it's a deeper, more fundamental version of, where do I come from?
Yet for most of human history, the answers to such an apparently simple question could only be attempted by religion.
It wasn't until the middle of the 20th century that science built a coherent and persuasive creation story of its own. It was a story based on theory, predictions, and observation. A story that could finally explain what had happened at the very beginning of time, the beginning of the universe itself.
A little over 100 years ago, if scientists considered the life of the universe at all, they considered it eternal, infinite, and stable. No beginning and no end. So even framing the question about the origins of the universe was impossible. But at the beginning of the 20th century, that began to change. New discoveries shook the old certainties and paved the way for questions about where the universe came from. One observation transformed our idea about the true scale of the universe. It began with a mystery in the sky. By the early part of the 20th century, it was well known that our solar system lay within a galaxy, the Milky Way.
Every single star we can see in the sky with the naked eye is within our own galaxy. And until the 1920s, all these stars, this single galaxy, was the full extent of the entire universe. Beyond it was just an empty void.
But there were some enigmatic objects up there as well, just discernible to the naked eye, that looked different. And one of the most notable is Andromeda.
You can find Andromeda if you know where to look. So if you start from Cassiopeia, those 5 stars shaped like a sideways letter M, if you move across from the point, one of the points of the M, and slightly up is where you should find it. Now, I'm going to use my binoculars to help me in the first instance. And if I zoom across, yep, there it is. You can tell it's not a star. I mean, it's basically a very faint smudge stuck between those two stars. That's it straight up there. That's M31, the Great Andromeda Nebula. Now, they were called nebulae because they had this smudgy, sort of wispy, cloudy nature. In fact, the word nebula derives from the Latin for cloud.
These indistinct objects were found scattered throughout the night sky. Telescopes revealed many of these nebulae were far more complex than simple clouds of interstellar gas. They appeared to be vast collections of stars, and that raised two intriguing possibilities.
Were these stellar nurseries places where stars were born and therefore residing within our own galaxy? Or, much more profoundly, were these beautiful, enigmatic objects galaxies in their own right, sitting way outside the Milky Way?
The implications of that second possibility were enormous. If true, it would instantly and utterly transform our idea about the size of the universe.
Here was an opportunity for an ambitious astronomer to make a real name for themselves. Perhaps someone with a really big telescope. Step forward this man, Edwin Hubble, a man from Missouri. Although, if you'd ever met him, you'd never have guessed, because he developed this weird persona, a pipe-smoking tea drinker with a very affected, aristocratic English accent. Hubble is probably the most famous astronomer ever, not least because of his consummate skill at self-promotion, but also because of the incredible measurements he would make.
In Hubble's day, when it came to observations and new discoveries, size mattered. Today, this is the most powerful optical telescope in the world, the GTC, with a primary mirror over 10 meters or 400 inches in diameter, far bigger than anything Hubble had.
In September 1923, Hubble was working at what was then the biggest telescope in the world, the 100-inch Hooker telescope at the Mount Wilson Observatory, perched on top of the high Sierra Mountains overlooking Los Angeles in California. He was using the telescope to study one of the most prominent nebulae in the sky, the Andromeda Nebula.
The same nebula I looked at earlier, and it was while observing it that one very special star caught Hubble's attention, one that could reveal the true nature of Andromeda. And I'm going to use this telescope to look for it now.
This is the control room of the GTC, and tonight they've pointed the telescope at Andromeda, and they're going to take a picture of it. It takes about a minute for the exposure to give you a clear enough image.
That's right. Takes a minute, yeah. Now the picture is finished, so we are going to open it.
Okay, so this is Andromeda here.
That's Andromeda, that's right. Yeah.
And now this is Hubble's original plate. Yeah. Right, now Hubble's star is down here in this corner. Can you find it in your image?
Yeah, if you take the image and you compare it, you will see that we don't see that one. What we see is the edge of the galaxy, so we have to go a little bit further away.
Oh, I see. So all this is just the edge?
That's the edge.
I was assuming it was the center of the galaxy.
No.
It just goes to show how much more resolution your telescope can get.
Yes.
Okay, so can we see that particular star?
Yeah, in order to find that particular star, because it's so faint, we have to look for reference which are brighter. And in this case, you will see 4 stars in here, which are these 4 stars, and the star Hubble found will be this one here.
That's it. That's
That
Hubble's.
tiny star is the one that Hubble found.
That's amazing. And are you able to get a magnitude for that star?
Yeah, we have to do a little bit of processing on the image, but we are able to get it.
Okay.
Hubble had found his star. He knew it was special because he compared his plate with others taken over previous nights. And he noticed that his star changed in brightness. Some nights it was brighter, some nights it was dimmer. He realized this is a variable star, and he saw the significance of it. He could see that this was real astronomical gold.
His star was a Cepheid variable. In the stellar bestiary, Cepheid variable stars hold a very special place. Because by studying the way their brightness changes, astronomers can calculate how far away they are.
Hubble's Cepheid was the first to be discovered in a nebula, so he knew that if he could measure its period, he'd be able to work out its distance from us.
So Hubble set about meticulously measuring how his star's luminosity varied.
It's not hard to imagine how exciting this must have been for Hubble. At his fingertips was the opportunity to resolve a fundamental yet simple question. Was this nebula within the Milky Way or beyond it? The answer would reshape our knowledge of the universe. Hubble measured the luminosity or brightness of his star over many nights and plotted this curve here. Now, when we measured it tonight, we found it had a value of 18.6. And I know because they measured it last night to be slightly dimmer that it falls on this side of the curve. But more important is the period, the time in days from peak brightness to peak brightness. Hubble measured this to be 31.415 days. This is the critical measurement.
Armed with this and its apparent brightness, Hubble calculated the distance to the Andromeda Nebula.
It was immediately apparent that this star is very far away. But when Hubble did his calculation, he worked out that it was 900,000 light years away, making this star the most remote object ever recorded.
It could mean only one thing. Not only is Andromeda a galaxy in its own right, but it lies well beyond our own Milky Way. And the myriad of other elliptical and spiral nebulae were also individual, distant galaxies.
It was a moment in human consciousness when the universe had suddenly and dramatically got considerably bigger. With this observation, Hubble had redrawn the observable universe.
It might not have directly challenged the idea of a stable universe, but it shattered long-held assumptions and opened the possibility of other, bigger secrets, like an origin to the universe.
Into this profoundly expanded cosmos strode someone who would, without realizing it, provide the tools to unlock that secret. This guy. A story as great as one that explains the origins of the universe would somehow feel wrong without involving a scientist as great as Albert Einstein. And so, of course, it does, because it was Einstein who provided the theoretical foundations needed to study the universe and effectively invent the science of cosmology.
100 years ago, he proposed his general theory of relativity. It turned physics on its head and gave us a completely new understanding of the world. He proposed that gravity was caused by the warping or bending of space-time by massive objects like planets and stars. His theories were revolutionary. Einstein was a maverick who ignored the conventional to follow his own remarkable instincts.
One of his lecturers once told him, "You're a smart boy, Einstein, a very smart boy.
But you have one great fault. You do not allow yourself to be told anything. Of course, it was this very quality that would allow him to change the world of physics, and of course to mark him out as one of the greatest thinkers of the 20th century.
And in 1917, he took his general theory of relativity and applied it to the entire universe.
By following the logic of his theory, he arrived at something rather unsettling. The combined attraction of gravity from all the matter in the universe would pull every object in the cosmos together, beginning slowly but gradually accelerating until gravity would ultimately and inevitably lead to the collapse of the universe itself.
But Einstein believed, like virtually everyone else, that the universe was eternal and static, and certainly wasn't unstable or ever likely to collapse in on itself. But his equations appeared to show the opposite.
In order to prevent the demise of the universe and keep everything in balance, he adds this in his equation: lambda, or the cosmological constant. It's a sort of made-up force of anti-gravity that acts against normal gravity itself. Now, he had no evidence for this, but it helped ensure that his equations described a stable universe.
Within his grasp was the secret to the origins of the universe. Yet Einstein simply couldn't or wouldn't bring himself to accept the implications of his own equations.
With hindsight, it seems remarkable that Einstein did this. I mean, here was a man who had revolutionized science by rejecting conventional wisdom. And yet, he couldn't bring himself to trust his own theory. He felt compelled to massage his equation to fit the established view. He even admitted that the cosmological constant was necessary only for the purposes of making a quasi-static distribution of matter, basically to keep things the way they were. Whatever his reasons, this little character lambda would return to haunt him.
Because while it prevented Einstein from understanding the implications, his ideas opened the way for someone else to propose a theory for the origin of the universe. He was a young, part-time university lecturer of theoretical physics.
His idea was so radical, it shocked the world of physics and split the scientific community. He started an argument that wouldn't be resolved for half a century. His name was Georges Lemaitre. Now, the eagle-eyed might spot the dog collar. In fact, he was both a physicist and an ordained priest. Of this apparently curious dual role, Lemaitre said, "There were two ways of pursuing the truth. I decided to follow both." And using Einstein's theory of relativity, he developed his own cosmological models.
Lemaitre's model described a universe that, far from being static, was actually expanding, with galaxies hurtling away from one another.
Furthermore, Lemaitre saw the implications of this. Winding back time, he deduced that there had to be a moment when the entire universe was squeezed into a tiny volume, something he dubbed the primeval atom.
This was essentially the first description of what became known as the Big Bang Theory, the moment of creation of the universe.
These were revolutionary ideas, and so he published them in the Annales de la Société Scientifique de Bruxelles, where they were promptly ignored by the scientific community.
So he travelled to Brussels to try to gain support for his idea.
The 1927 Solvay Conference, held here in Brussels, was probably the most famous and greatest meeting of minds ever assembled. But for our story, the most significant meeting didn't happen here. It wasn't planned and happened away from the conference.
It happened here. In this park, the unknown Lemaitre approached the most famous, the most fated scientist in the world, Albert Einstein.
Here, finally, was his chance to explain his idea about an expanding universe to the very person whose theory he'd used to derive it. You can only imagine Lemaitre's trepidation as he approached. If Einstein endorsed his radical idea, then surely it would be accepted. Surely this brilliant mind, this titan of physics, this deeply original thinker would see the merits of his theory. But after a brief discussion, Einstein rejected his idea out of hand. According to Lemaitre, he said, "Vos calculs sont corrects, mais votre physique est abominable." As far as Einstein was concerned, his maths might have been correct, but his understanding of how the real world worked was, well, abominable.
Once again, Einstein dismissed the idea of a dynamic universe.
Lemaitre's paper should have ignited science, but without the backing of such a huge and influential figure as Einstein, his groundbreaking idea was doomed to be quietly forgotten. Unless some observation or evidence showed up to support the idea of an expanding universe. Edwin Hubble here was riding high after his discovery that proved there were galaxies outside of our own. He was feted by Hollywood glitterati, a guest of honor at the Oscars, and with access to the world's most powerful telescope, he was ready for his next challenge.
He'd heard of some unusual observations, that many galaxies appeared to be moving away from us. No one could understand why this might be. So in 1928, the world's most famous astronomer turned his attention to this new cosmic mystery and began to measure the speed that these galaxies were moving relative to Earth.
To measure the velocity that a galaxy was receding from us, Hubble used something called redshift. Now, it's not a perfect analogy, but the effect is similar to one most of us are familiar with in sound. The pitch of a car engine as it approaches us is higher because the sound waves are compressed, but the pitch drops lower as the car recedes because the sound waves are stretched. The effect is similar with light waves. As the source of light moves towards us, the observed wavelength is squashed towards the violet or blue end of the spectrum. But if the source is moving away from us, the wavelength is stretched towards the red end of the spectrum, or redshifted in the parlance of astronomers. And the greater the velocity the object is receding, the greater the redshift.
With his assistant, Milton Humason, Hubble spent the next year carefully measuring the redshift of galaxies. And I've got the chance to do the same thing right now using this telescope.
Okay, Massimo, have you found a galaxy for me?
Yes, I found this galaxy.
So how far away is this?
It is approximately 430 megaparsec far.
So if you convert that to light years, so 430 times 3.26, so it's about 1.5 billion light years away.
Yeah.
Okay. Hubble needed to measure the average light coming from the galaxy in order to get a spectrum so that he could calculate the redshift. Now, Humason did this by exposing a photographic plate, and it took him a whole week to collect enough light to get the spectrum. But here at the TNG, the Galileo telescope, they use instead a very sensitive chip that can do this much more quickly. How long does it take for you to get a spectrum?
Approximately 10-15 minutes exposure.
So, 10 or 15 minutes exposure compared with a week back in Hubble's time. Far more powerful than anything they had back then. It's done.
That is the spectra is quite good. Is
Okay, so this is the raw spectrum that's been
Yes.
taken. Is there a particular emission line here that you will use as your reference to measure the redshift?
yeah. Here, for example, you have an emission line, but to obtain a real spectra, you have to clean it to obtain the final one.
This is the cleaned up.
Yes.
Version of that.
Yes, of that.
So this is the actual
Emission lines.
emission lines from the galaxy.
Yes.
And this one below, I guess, is the reference.
The reference, so correct, of a galaxy with a redshift 0.
Okay, so one that isn't moving away relative to us.
Yes.
And so it's very clear here, if you compare the top one with this one, every emission peak
Yeah.
is shifted.
Is shifted in the red. The reference line for example is H alpha. From this, you can compute the redshift of this galaxy.
And can you work out from that how fast the galaxy is moving away from us?
In principle, you can obtain this.
Okay, so what's the formula?
The formula is the difference between the rest wavelength and the observed wavelength divided by the reference wavelength and multiplied by C. This is the Doppler effect.
Let's see if we can do that roughly.
Yes.
Okay, so this is about
7, 2, 0, 0, approximately.
okay,
Minus
6,
5,
6, 3.
3, 3
Okay.
over
6, 5, 6.
3.
Yeah.
And that's the fraction of the speed of light.
Yes.
Okay, so I might as well do this. I should do it with my calculator. So 7200, 6563. So it's a 7, 3, well, that's a 6. Okay, so then that we divide by 6563. Okay, so it's roughly 0.1 the speed of light. 0.1 c. So it's about 30,000 kilometers per second. Yes?
Correct.
Thank you. Okay, I'm actually quite pleased with my maths here because I was under pressure. So this galaxy is 1.5 billion light years away from the Milky Way, and it's moved from the redshift. We've worked out it's moving away from us at 1/10 of the speed of light. That means it's moving away from us at 30,000 kilometers per second. Boom. Science.
Once he'd calculated the speed of the galaxy, Hubble then measured how far away it was.
Once Hubble had both his measurements, he could start plotting them on a graph of velocity against distance. Now, he made 46 different measurements, and when he put them on the graph, he noticed a pattern emerging. He could draw a line through all these points. Each one of them is an individual galaxy. He noticed a connection between the velocity and the distance of a galaxy. In fact, the further away it was, the faster it was moving away from us.
In a stable universe, the speeds of galaxies should appear random. You wouldn't expect a clear relationship between the distance of a galaxy and its velocity. Hubble's graph showed that the universe was expanding, which had profound implications for the idea of a beginning to the universe.
What this means is that it's not just that the galaxies are all speeding away from us and from each other, but if you could wind the clock back, there would have been a time when they were all squeezed together in the same place. Here finally was the first observation, the first piece of evidence that Lemaitre's idea of a moment of creation, of a universe evolving from a big bang, might be correct. Thanks to Hubble's work, Georges Lemaitre, the unknown Belgian cleric, the theoretician without proper international credentials, the man whose physics Einstein called abominable, was belatedly rightly recognized for his bold theory.
Most significantly, the biggest name in physics came around to this revolutionary idea.
In 1931, on a visit to Hubble's observatory, Einstein publicly endorsed the Big Bang expanding universe model. The redshift of distant nebulae has smashed my old construction like a hammer blow, he said. Einstein dropped the cosmological constant. He even wrote to Lemaitre, "Ever since I introduced the term, I have had a bad conscience. I am unable to believe that such an ugly thing should be realized in nature." It must have been quite an absolution for Lemaitre. Having been practically cast out into the scientific wilderness, he was now firmly at the center of a cosmological revolution.
The idea of the Big Bang was finally gaining traction. But despite Einstein's seal of approval and the observations of Hubble, the argument was far from over.
There were still significant objections if the idea of a Big Bang was to be widely accepted. A scientific theory of creation isn't just about explaining the expansion of the universe. There are more profound issues to resolve.
The problem was, the Big Bang raised as many questions as it answered. Like if the universe had erupted from a single point, where did all the matter come from? To go further, the Big Bang theory needed to explain how matter itself had been formed.
Well, before that could be answered, we need to know what the universe is actually made of, the elemental building blocks. And working that out took an incredible bit of insight by a remarkable woman, Cecilia Payne. She studied at Cambridge University but wasn't awarded a degree because, well, she was a woman. So to continue her studies, she needed to go somewhere more enlightened. She left England for America, and it was there that she revealed the composition of the universe. If you were to ask someone what the most common elements were, an atmospheric scientist might say nitrogen. After all, it makes up more than 3/4 of the atmosphere. Geologists might say silicon or iron or oxygen, which all seems very quaint and Earth-centric and really rather parochial.
So, astronomers thought it better to look at the sun, which makes sense given that most of what we see when we look out into the cosmos is stars.
The first attempts to analyze the composition of the sun were done with a setup rather like this. Well, not exactly like this. This is a cutting-edge 21st century solar telescope. But the basic idea was exactly the same. The basic idea is very simple. The sun's light is reflected off this mirror here up into a second mirror, where it bounces off down through the top of the tower all the way to the bottom 10 stories down, where it's focused and split into a spectrum and analyzed. This is the control room of the solar telescope. The base of the telescope is over there. And here I've got a live feed image of the sun. And what I've got up here is a zoomed in section of the spectrum of the light coming from the sun. Now, it's in black and white, but it actually corresponds to the green part of the spectrum. And these two thick, dark lines correspond to the element iron. They tell us there's iron in the sun. Now, here I have the spectrum in much more detail, and these two lines correspond to these two dips in the absorption spectrum at very specific wavelengths. This is iron. If I look at different parts of the spectrum, I can see other elements too. This big dip here is hydrogen. These two dips represent oxygen, and this dip corresponds to the element magnesium.
All these dips and lines in the spectrum indicate the presence of these elements in the sun's atmosphere, effectively a fingerprint of the sun's composition.
To a geologist, these elements are all very familiar. It appears at first glance that the sun is made of the same stuff as the Earth, that the sun is simply a very hot rock.
And that would have been that, were it not for the insight of Cecilia Payne. She realized that the spectrographs were being affected by processes in the sun's atmosphere. These would distort the apparent abundance of the elements that make up the sun.
So she recalculated the relative abundances of the elements and discovered that the sun was composed almost entirely of just two elements, hydrogen and helium. All the other elements, carbon, oxygen, sodium, iron, that made the sun seem so Earth-like, amounted to just a tiny fraction of its composition. When she first presented this result, it was considered impossible. In fact, when she wrote up her work, she was persuaded to add the comment that these calculated abundances of hydrogen and helium were almost certainly not true.
The idea was only accepted some 4 years later, when the director of a prestigious observatory arrived at exactly the same conclusion by different means.
Ironically, this director was the very same man who'd initially dismissed Payne's work as clearly impossible.
Payne's revelation about the ratio of hydrogen and helium was found to be remarkably consistent for almost every star in the galaxy.
That led to a big conclusion. The universe is dominated by just two elements, the simplest and lightest elements, hydrogen and helium. Together, they make up more than 98% of all the matter in the universe. All the other elements that are so important to us, like carbon, oxygen, iron, amount to less than 2%.
So now, the challenge for supporters of the Big Bang Theory was very clear and simple. Could the Big Bang Theory explain the creation and the observed ratios of hydrogen and helium found in the stars? But to answer that would require a fundamental shift of emphasis.
Rather than consider the almost infinite vastness of the universe, it was necessary to consider the infinitesimally small world of the atom. And that required not an astronomer, but an entirely different kind of physicist. George Gamow was a Russian nuclear physicist and an enthusiastic advocate of the Big Bang idea. He turned his attention to the earliest moments of the universe. Here, he felt, was where the answer to the composition of the universe lay. This was when he believed hydrogen and helium were first forged, and he proposed it would have happened very soon after the birth of the universe.
He set about building a mathematical model of the earliest stages of the universe.
He was thinking about the universe in terms of seconds and minutes rather than billions of years. And he recruited a young protege, this chap, Ralph Alpher, to help him. After years of hard work, some of which, according to Alpher, were aided by hard drinking in a bar, they presented their idea. By rewinding the universe, it was clear to them that there would have been a time when the early universe was incredibly dense and phenomenally hot. At this stage, which they calculated to be just 3 minutes after the Big Bang, the universe would have been so hot that atoms themselves couldn't exist, only their constituent parts. A kind of superheated primordial soup of protons, neutrons, and electrons. They even gave the super name, ILEM, from an Old English word for matter.
Then came the crucial moment. A time when conditions were right for the nuclei of the first elements to be forged.
In a short period of time, which they estimated to be less than 15 minutes, hydrogen nuclei, protons, were coming together to form helium in the process of nuclear fusion.
Moreover, the ratios of hydrogen and helium predicted by their model matched that measured in the stars. They announced their results in a paper published in 1948.
However, Gamow added another author to the paper, the famous nuclear physicist Hans Bethe, who had nothing to do with the work. Gamow added his name for a laugh. He thought it made a good science pun, because the authors of the paper now read Alpher, Bethe, and Gamow.
The young Alpher, however, was less amused to be sharing the credit with someone who'd done no work.
By way of reconciliation, the story goes, Gamow produced a bottle of Cointreau for Alpher, but with the label changed to read ILEM.
The ability to make calculations that explain the origins of matter in the first few minutes after a Big Bang was remarkable in itself. But there was a very significant prediction that emerged from their work. A prediction that had the potential to deliver the proof that the universe had begun with a Big Bang.
Alpher continued to study the early evolving universe, focusing on what happened next. He pictured the universe at this stage as a seething fog of free electrons and atomic nuclei. Then it dropped to a critical temperature, a temperature cool enough for electrons to latch on to the nuclei of hydrogen and helium. At this precise point, light was released to travel freely throughout the universe, the first light of creation. This might have remained nothing more than an academic curiosity had it not been for Alpher's insight. You see, he realized that this light from the beginning of the universe should still be reaching us now, after billions of years. Very weak, very faint, but observable in all directions. He calculated that the expansion of the universe should be stretching the wavelength of this light beyond the range of the visible spectrum and should now be arriving as microwave radiation. So, find this predicted ancient microwave signature and it will prove not just the theory of the early evolution of the universe, but the entire Big Bang theory itself. Simple. The problem was, this was the late 1940s, and no one had any way of detecting such a weak signal.
The acid test was quietly forgotten. Supporters of the Big Bang now had the prediction and observation of an expanding universe, and a theory for how elements were forged in the first few minutes after the Big Bang. But without the clinching evidence for this, the argument over whether the Big Bang theory was correct rumbled on.
The opponents of the Big Bang continually tweaked and adjusted their theories to make their idea of an eternal and infinite universe fit the new observations.
The scientific community was still pretty evenly split.
Conclusive proof of the Big Bang theory would eventually emerge some 15 years later. It would be revealed quite unexpectedly.
by two young radio engineers. In 1964, Arnau Penzias and Robert Wilson, that's Penzias on the right there, discovered something so momentous it won them the Nobel Prize.
This telescope is dedicated to study their accidental discovery.
In 1964, Penzias and Wilson were working at the Bell Laboratories in the US, where they were given this, a bizarre and obsolete piece of kit to play with. It looks, for all the world, like an enormous ear trumpet.
But when they turned their telescope on, they found that the sky was saturated with microwave radiation.
All warm bodies emit microwave radiation, whether it's from the atmosphere or from the instrument itself. And of course, today's mobile communications flood the sky with it.
So, before they could do any useful measurements, they had to calibrate their horn antenna to see if they could reduce this noise.
Even after accounting for the atmosphere and their instrumentation, of course there were no mobile phones to worry about back then, they were still left with this persistent and deeply irritating background noise. It was registered on their instrument as a radiation with a constant temperature of 3 degrees above absolute zero. A microwave hiss that they couldn't get rid of no matter what they tried.
Even more annoying for them was the fact that it seemed to be everywhere they pointed their celestial ear trumpet.
They were about to give up when Penzias attended a meeting where he casually mentioned this irritant to a colleague. A few weeks later, the same colleague phoned him up and said he knew of some researchers in Princeton who were looking for just such a signal. Unwittingly, Penzias and Wilson had stumbled upon that predicted radiation, Alpha's burst of light from the early evolution of the universe. Here, at last, was proof of the Big Bang Theory. It's quite remarkable to think that this microwave radiation has travelled across the furthest reaches of space from 13.8 billion years ago, when that first light from the Big Bang was released. As Penzias himself said, when you go outside, you're getting a tiny bit of warmth from the Big Bang on your scalp. And yes, I probably feel it a bit more than most.
Almost 40 years after Lemaitre first postulated it, the idea of the Big Bang had finally entered the scientific mainstream. But the discovery of this cosmic microwave background radiation, the CMB, and the proof of the Big Bang Theory itself isn't the end of our story. We've probed back to the first few minutes after the Big Bang. And beyond this lies a new frontier of knowledge.
There are still very big questions to resolve about the beginning of the universe. Questions like, where did all the matter itself come from? And how do you get something from nothing? The answers to these questions lie further back, hidden behind the curtain of the CMB. Their secrets lie in the primordial universe, within the very first second of its existence.
This is where the edge of our understanding now lies. And this is where scientists are focusing their efforts. Not by looking into the skies, but here on the border of Switzerland and France. More specifically, at CERN, with the largest particle accelerator in the world, the Large Hadron Collider, or LHC.
Now, you might be wondering what a particle accelerator has to do with the early universe, because the connection between the two is far from obvious. The thing to remember is that when the universe was very young, it was much smaller. And so all the matter, everything that makes up the stars, the galaxies, black holes, all had to be confined into a much smaller space. At that stage, the universe was phenomenally hot, and more significantly, its energy density was very high.
It was then that the first matter sprang into existence. The LHC can't yet replicate that process, but it can allow us to study the properties of these fundamental particles.
Once a year, the LHC stops its normal business of colliding beams of protons and instead uses much more massive particles to create collisions with energies more than 80 times greater than that produced from two protons. They do this by accelerating atoms of lead, stripped of all their electrons, up to speeds close to that of light, and smashing them together. And that lets us see something pretty special.
The collisions are so intense that for a moment will create something unique. A world not of atoms or even neutrons and protons, but of quarks and gluons and leptons, exotically named particles that came together to form atoms in the first millionth of a second after the Big Bang, and have been locked away ever since.
Down there, underneath that lead shielding, we're recreating a stage in the universe's evolution called the quark-gluon plasma. Now, this is the moment immediately before the quarks become trapped by the gluons to create protons and neutrons, which themselves go on to form the nuclei of atoms. The phrase we use grandly is the confinement of the quarks. To develop the necessary energy, the lead nuclei are passed through a chain of smaller accelerators, gradually ramping up the energy until they're finally fed into the largest accelerator on Earth, the LHC. Now, the maximum energy a beam can achieve is directly related to the size of the accelerator, and the LHC has a circumference of 27 kilometers. Now, that means the beams here can achieve an energy of 1,000 tera-electron volts. Now, actually, that's less than you might imagine, because it's equivalent to the energy that a housefly hits a window pane. But the critical difference here is that the energy is concentrated. It's the energy density that's important. The LHC can squeeze all that energy down to a space that's less than a trillionth of the size of a single atom.
This is something that can happen nowhere else in the known universe.
The two beams of lead nuclei are traveling around the ring in opposite directions. They're meeting deep underneath this control room at the detector. You can see live feed pictures of the detector up on that screen. Now, underneath us, they're traveling at a speed of 99.9998% the speed of light. That means they're covering the full 27-kilometer circumference of the ring more than 11,000 times per second. When the beams reach maximum energy, and we can see up there it says iron physics stable beams, that means they can be crossed, just like in Ghostbusters. At that point, a tiny fraction of the lead nuclei will collide and create a super hot, super dense fireball with a temperature 400,000 times hotter than the center of the sun, and a density that would be equivalent to squeezing the whole of Mont Blanc down to the size of a grape.
That looks like a fantastic image there. So can you tell me what we're seeing?
It's amazing, actually, isn't it? It's literally tens of thousands of particles and antimatter particles flying out. There's kind of aftermath of this explosion.
Right. So the coloured particle trails here aren't the quarks and gluons themselves, but evidence of the quark-gluon plasma created by the collision.
We have to infer its properties from looking at the debris that flies out. It's a bit like working out how an aircraft works by looking at the debris of a plane crash. That's what we see.
What I find amazing is what we're doing here is trying to recreate that moment in the early universe where the quarks and gluons were all free to float around because the energy was so high, and then it cooled and they stacked together. You're doing the opposite. We're starting with normal matter, smashing it together, and going back to that unconfined state, that plasma.
Yeah, I mean, I like to think of Alice as a time machine. We're actually winding back the clock. And this is the only way that we can study the properties of free quarks, because these quarks have been imprisoned inside particles like protons and neutrons for 13.8 billion years.
That's pretty incredible, isn't it? Finally, after 13.8 billion years, you can set these quarks free, even if it's for a fraction of a second.
Yes.
While we don't yet know how matter sprang into existence, studying these collisions allows us to make the first tentative steps towards that discovery.
What we've just witnessed is the earliest stages of the universe that anyone, anywhere, has been able to observe. It's the closest we've got to the moment of the Big Bang. And let's face it, it's not bad. 1/1,000,000th of a second after the Big Bang itself.
Even going this far back in time still leaves physics with unanswered questions.
Beyond this is where some of the deeper mysteries of the universe are hiding. How the four fundamental forces that bind matter together, gravity, electromagnetism, and the nuclear forces, are connected to each other. How the particles that make up matter itself condensed out of a fog of energy. How mass is generated from the force that binds protons and neutrons together. And how the universe itself underwent a super-fast expansion in 1 billion of a second to create the structure of the cosmos.
At the moment, we have no way of observing any of these phenomena. This is the realm of abstract theory and speculation.
If we're ever going to replicate this early stage of the universe's evolution, we're going to need to create considerably higher energies. Frankly, we're going to need to build a bigger collider. And that's a problem. And it's not just one of expense, although it would be phenomenally expensive.
No, it's more one of finding the room to build it.
Remember when I said the energy is related to the circumference of the accelerator? Well, the LHC down below me has a circumference of 27 kilometers. It runs beneath the Jura Mountains and straddles both France and Switzerland. In order to look back and observe the universe at this earlier stage, well, we need to build an accelerator with a circumference larger than the orbit of Pluto.
Revealing the origin of the universe begs another, even more profound question. How will it end? Next time, I discover whether the universe will end with a bang or a whimper.
Want to discover more about the beginnings of the universe? Then go to the address below and follow the links to the Open University.
Let 5 Live's Naked Scientists bring you the very latest from the world of science. Download them using the BBC iPlayer radio app. And stay with us on BBC4. Louis Theroux's in the USA, exploring education and autism in Extreme Love next.